We will have a look now at random sparse matrices. And here you see a random sparse matrix of size 100 by 100. It has 982 non-zeros and a density of 9.8%. The density is D. And we created that by using a random number generator from the book Numerical Recipes. So you generate a random sparse matrix, for instance, by choosing for every element independently and from a uniform distribution, whether it is 0 or not. And if the probability of creating a non-zero is D, then you expect that altogether there will be D n squared non-zeros in the matrix. And random sparse matrices, they have a very special property. If you take a fixed part of the matrix, for example, a block, then there's an expected number of non-zeros that are there. And that's a special property, and you can use that for analyzing algorithms involving these random sparse matrices. This is not a random sparse matrix. It has a pattern. You may be familiar or unfamiliar with the pattern, but this is a structured non-random matrix. Now, we all know the expression a random person. We use that sometimes, and it means an unfamiliar person, unexpected, some other properties unknown. But in the context of sparse matrices, a random sparse matrix or a random graph has a very specific meaning. It has a structure and the property that we just mentioned. So when we look at random sparse matrices for multiplying a sparse matrix with a vector, then we first create the sparse matrix, and we can do that by for every element we draw a random number, Rij, and then if Rij is less than the density, then we create a non-zero. And after that, we can distribute this matrix, for example, by using a distribution that's independent of the sparsity pattern. It could be a square block distribution, square grid distribution, square cyclic distribution, or a cyclic row distribution. And we can analyze the result. A question then is, what will be the computational load balance? And that really is the question asking for how many non-zeros does the processor have that has the maximum. We cannot exactly solve this, but we can give a bound a bound on the probability that the maximum exceeds a certain value. And we can do that by a theorem by Chernoff from 1952. And the theorem says the following. Assume that we have a density which is a number between 0 and 1 exclusive, and that we have m independent Bernoulli trials, x0, x1 up to xm minus 1. And in each trial, we get a result xk, where the probability that it is a 1 is d, and otherwise it will be a 0. So then we can define x as the sum of all those xk's, and mu as the expected outcome, which is the number of trials times the density. Then Chernoff gives a bound, and the bound says the probability of x exceeding 1 plus epsilon times this mu, the expected outcome, is less than, and now we get a big formula, e to the power epsilon divided by 1 plus epsilon to the power 1 plus epsilon, and all of this to the power mu. Now a question to you. What is the probability of getting more than twice the value mu? Well, this is a simple substitution once you realize that getting twice the expected number mu corresponds to epsilon equals 1. And then you substitute, and then you get e to the power 1 divided by 1 plus 1 to the power 1 plus 1, which is 4. So it's really e divided by 4 to the power mu. And e divided by 4 is about 0.68. OK, we can apply this to a random sparse matrix. The expected number of non-zeros, so mu, is just d, the density, times n squared divided by p. And that's n squared divided by p is the number of elements that a processor handles. Elements whether 0 or not. Multiplying by d gives the expected number of non-zeros that a processor handles. And then ES is the probability that processor S exceeds 1 plus epsilon times mu. Now, of course, for all processors, this probability is the same. We call it Q. And then E is the event that one of the processors exceeds this 1 plus epsilon times mu. And that processor, of course, and the processor that has the most, determines the outcome. So we can give an expression for the probability of this event E, because if no event ES occurs, then none of the processor exceeds this. That probability is 1 minus q to the power p. Every processor has a probability 1 minus q of not exceeding, and all of them not exceeding is then 1 minus q to the power p. And then the probability that this does not happen, so that one processor exceeds the bound, that is then 1 minus q to the power p. OK, so this gives us actually a statement on the expected cost of the local sparse matrix vector multiplication, which is super step 1 in our algorithm, in our parallel sparse matrix vector multiplication algorithm. And there we see this expression appearing. And then for q, we substitute the Chernoff bound. And then we get a function, which is a function, obviously, of epsilon. OK, so here you see the measured probability of exceeding the normalized cost. So we have this bound, which is the dashed line. On the other hand, if we just sample a lot of matrices, in this case we created 100,000 matrices, and each time we measured how many, whether there are processors exceeding a certain bound. So we can see what is called the normalized cost of this particular matrix with the given distribution is. And then we put them in a picture. And then you see that in general, the situation is better than the bound predicts. Well, that's what it is a bound for. And we expect, if we get the best distribution, then every processor would have, for this problem, 100 non-zeros, because we have a matrix of 1,000 by 1,000 with a 1% density and 100 processors. But the most occurring is that we have 124. That's about 9% of the cases we have a maximum of 124. And then this maximum goes down quickly. OK, so having looked at the computation cost, we now look at the communication cost. The communication cost, if the density of the matrix is high, will be very close to that for a dense matrix. But the computation cost will be lower, and that's what makes this a hard problem. Communication will be relatively expensive for random sparse matrices. And here you see this visualized. We have two processors. This is our original 100 by 100 matrix. And we have permuted the rows and columns because rows that were completely assigned to the red processor, we moved to the top, completely assigned to the blue processor to the bottom, and those that were split, and that means with communication, we moved to the middle. And we did the same for columns. And then you see the middle is quite big. And that's an indication that this is a hard matrix to partition. So we have a BSP cost then of a 982 plus 45 times G plus 4 times L for this matrix. And the 982 is, we have a good load balance, but we have a lot of communication here. This form of the matrix we call the separated block diagonal form, SBD form. So it's very useful for visualizing the outcome of a partitioning. You can also do this for more processors. And it can also be used in sequential computing because it has a nice property for the cache of a computer. If, for example, you cannot store the whole vector v, the input vector, in the cache, but only part of it, then if you're lucky in the beginning with the red part, everything is still in the cache. And at the end, with the blue part, also everything is in the cache. And in between, you move gradually, you move part of the vector out and another part in. And that way, it is cache friendly. Here we have some results where we compare just a Cartesian distribution, for example, a block distribution of a random matrix, which gives a certain epsilon, which you see in the column on the left. You see, for example, for 32 processors, you get for this particular matrix an epsilon of about 12%. And then we can also use the Mondriaan distribution, which really takes the random sparse matrix, tailors a good distribution to it, and you have to specify from the beginning what epsilon that is acceptable to you. And there we take the same value as for the Cartesian distribution. And then you see that we reduce the communication volume by a factor of about 2. But still, there's a lot of communication here. To summarize, random matrices, if you distribute them, in general, you get a good load balance. You can quantify this by using the Chernoff bound. You can improve it a little bit by using a Taylor distribution, like, for example, using Mondriaan partitioner, but it remains a hard problem with relatively much communication. So the final question. Assume that we have a random sparse matrix, n by n, density d, and we have vectors, input vector v. We want to compute the output vector u, is a times v. And we have the distribution that we've seen before for dense matrices, where the matrix diagonal is distributed in a cyclic fashion, the vectors also. That's the system. And then I would like to know, for the first, the communication superstep, the fan-out of this parallel sparse matrix vector multiplication, what is the expected cost? You will need a little bit of elementary probability theory to answer this question.